Now I'm recording. Yeah, so by watching the video recording here, you'll be able to, catch up. And then by, checking some of the reference videos that will be added, you would also be able to catch up. So yeah, let's get started. I'll be sharing my screen. The last class would essentially, be a general roundup and maybe a small quiz, and that will be next week, right? And after next week, we will have a break of about 2 to 3 weeks where we will throw out problems that you could pick as a problem set to what you may want to solve for the hackathon, right? The prices for the hackathon is not set yet, but it could be as high as 500,000. Now there are a lot of big people here. 500,000 may not be, some interesting amount to a lot of people here, but it means something to some. But don't do it because of the money. Don't do it because of the prizes. Don't do it because of the what's available to win. But do it because of the passion, the interest, and the result you could create with the knowledge, right? So from the last class next week, we'll give a break of about 2 to 3 weeks, and then we'll start the hackathon. The hackathon will last 1 month long, right? And the last day of the hackathon will be a physical event in Ikeja where teams will be able to project, or teams that are physically present would be able to demonstrate what they have, and prizes will be awarded, right? So let's see your team come first, right? So what we're thinking of is 500,000 for first position, 300,000 for second, and 100,000 for third, right? You can collaborate with the leader of the team must be a member of African AI Foundation, but you can collaborate with external parties when you're forming team, and the team can be, you know, between 3 to 5 people essentially. Yeah, we should not see a team bigger than five. Yeah, but if you are a one-man team, that's okay. But ideally, I think a team should be minimum of 3 people. But if you can pull it off alone, then that's okay as well. All right, that is that on that. Concerning the hackathon and how we are rounding up the 2023 edition of African AI Foundation cohort. Again, I'm congratulating you for sticking through it. So I'll be sharing my screen. Let me know if you can see my screen.
Yes.
Thank you. Thank you.
Yes, I can.
Thank you as well, Mr. Sizua. All right. So I'll be getting started. Uh, Generative AI accuracy from a machine. This is the second series. We discussed last uh, everything. We kind of like dialed it back to, I think, the first or second class. Every form of knowledge we've created as humanity. We could reduce them to some sort of numbers, right? Whether those number represent those information conveyed in the actual information or not, but we could at least try, right? The information density may vary in terms of how much of uh, information is covered or condensed into those numbers, but at least we've been able to succeed in compressing information in any form to some numbers, right? And we did some examples here. Right here on my collab, we did some examples where we converted images to the very the numbers. This is not the embedding yet. This is just the pixel number, right? RGB, right? 0 for black, 255 for white, and then whatever is in the middle, right? We also converted. Okay, I don't think this is a recent stuff that was just added. Now this is converting image to an image embedding, extracting feature from an image, right? This is using VIT extractor from Transformer. We'll get to all of this shortly, right? So just hang in there. Uh, so also, okay, yes, we did for audio where we extracted the information, compressed in that audio. It could to you, to a human observer, you would be, hearing the statement being made in the audio, but to a machine, it has to be some, array of numbers, right? And we were able to show that, okay, this is what it looks like, when we did feature extraction, right? We used wave to vec. And then also we moved to tokenizers, that's for text, right? And we converted this particular word, convert this words to numbers. African AI Foundation is creating an army of AI champions, and then it gave us these numbers as the word embedding. We use the model BERT to do this, right? A lot of interesting questions came up that, okay, are these numbers random? How is it generating those numbers? And then the answer to that that was given last week was that they're not random. The uh, BERT model was trained on a number of literatures, right? And based on the literature that it has been trained on, it knows the relationship between words contained in those literatures, right? And it has, assigned tokens, not words, tokens, right? To those, it has assigned numbers to those tokens contained in the words. A token could be, a convert, right? Could be two tokens, right? Think of tokens as syllables. When Chat GPT-4, let's see, GPT-4 token size. I think it's about 1 tokens or so. What is the token size for Chat GPT-4? Chat GPT-4 token size. No, I don't think I'm using the right keyword. Training token size. Okay, cool. Right? That is 13 trillion tokens. Right? And that's because it contains some tokens, using programming languages, some tokens that is using non-English languages and all of those kind of things, right? So tokens can be, numbers, right? But so in this BERT model uses words, right? It converts. So if you count the number of words, right? So this 101 in BERT encoding is used to open a sentence, right? And 102 is used to close a sentence, right? 101, 102. We did okay, here we have some other BERT encoding. You see 101 opens all the sentences, right? 101. So it uses that to know that, okay, this is the start of a new sentence, right? And then if you look at it, 102 closes all the sentences, right? So it's a special, it is not random, essentially. That's what I'm trying to say. The numbers here are not random. It is a way of telling the machine that whenever you see 101, it's the start of a sentence, or whenever you are trying to convert, a start of a sentence to a number, here is the number to ascribe to it. This is the word, this is the number attached to this word, and all of that, right? So I would the external resource I would link will contain word to vec model. It's a simple method of converting words to vectors, right? How that happens is that all the words in a dictionary, right? You could have your own dictionary that, okay, you know what, my own dictionary contains 5,000 words or 1,000 words or 200 words, right? So all the words that would be used by your own embedding would be used to train the word to vec, and you will decide the dimensions that the vector should have, right? When we were in secondary school, I think sometimes in university as well, we did three axis vector IJK, XYZ a lot, right? Because we could relate easily to vectors in three dimensions, right? But technically speaking, vectors could be, hyperdimensional. We could have 200, dimensions of a vector. The first monochrome image that we trained was actually a vector with 784 dimensions. We cannot think of how that dimension looks like as human beings, because okay, I think I have my scratch pad here. I have my scratch pad here. Let me share. Let me. Okay. All right. So a word, if we, of course, two dimensions looks like this, right? So for a two dimension, uh, so this is your two dimension. You have your y axis here. You have your y axis here, and your x axis here, right? You have number pattern across, scattered across, right? That is your two dimensions, right? For three dimensions, it would look like something like this, right? It should look more like this, right? Let's say this is z axis, right? This is your y axis, and this is your, sorry, this is your x axis, and this is your y axis, right? So you could have points placed in three dimension, right? Points placed in three dimension. But how would you describe a dimension that is 20? It is almost impossible for humans to be able to conceptualize that. How do you want to do it? It's almost impossible for us to think. Mathematically speaking, it's actually a very easy problem, right? At the end of the day, all these things can be converted into matrices, do vector multiplication, do vector, addition, and all these kind of things, right? So that is what makes machine learning possible at the end of the day, really, because we have hyper dimensional problems, right? Things that are not in two dimensions, right? And we are able to represent them easily. So before we, go too much into, dimensions of all these problems, let me just open the slide. Let's go through this slide. So this is how we moved since 2010, right? Lesson one, we went as far back as 1967, right? The first time that the concept of machine learning was created. But we've caught all of that behind because the techniques were not that great, the methodologies were not that advanced. So starting from 2010, software was everywhere. Software was in your freezer, it was in your oven, was in your TV, right? Your everything essentially, right? APIs, software as a service, cloud, AWS, and all those things, right? So this is Anderson Horowitz's blog. Say software, why software is eating the world. So software was literally eating the world. In 2017, because of some of the problems that we stated in class two, right? Machine learning thrives so well when the domain is so complex and so unpredictable, where rules are too complex. If x equals to y and y is equals to b and b minus whatever, right? And that rule can change in a matter of seconds. Your classical software methodology fails. An example of a driverless car where you're using uh, you know, a classical software methodology to move your car on your streets, right? You'll be saying, okay, if dog, if there's a shape that looks like dog, God help you, you get the right representation for a dog. correct, and then right right representation for humans, and right representation for streets and all those things, right? And you would write your software in a classical way. But now deep learning helped us to be able to achieve better results than classical software, right? That's what we learned from class two, right? So methods like CNN, which Dr. Tulu took us through, recurrent neural network, we didn't really spend time there, right? But those are, neural network architectures. And LSTM, we didn't touch that at all, right? These are neural network architecture that allows us to be able to solve some specific problems, like CNN is for images, LSTM is for words. But the problem is that these architectures solved interesting problems at those times, but they could not scale. They could not scale so well, right? LSTM, for example, was having a problem called weight decay. It will be forgetting important information because that information was passed across 500 tokens away or 500 words away, right? So it's not paying so much attention to that particular word, right? Because the word was passed across 200 words away or 200 tokens away, it decays, as it's move across, sequences of words. And why CNN was great in doing so many things, right? Real life application could not, it could not scale to real life application where you want to do, real life image segmentation and, decision making on top of that, and, multimodal inferences on top of that, right? It's a very fantastic architecture, and it's even one of the architectures that allows for the advancement in the new architecture that works today, right? So everything that you have learned works. They formed the foundational structure for what you'll be learning today, essentially. So now 2022, from 2022, it changed. Not deep learning eating software anymore. Now transformers are eating deep learning, right? And we'll be going through that shortly, right? So these are transformer architecture. So these are some of the transformer models, vision transformer. What you're looking at in this code for that image, the feature from this image is a vision transformer, VIT feature extractor, right? So this is a vision transformer for image classification. It's from the transformer library that we installed up there, right? So vision transformer, wave to vec. Wave to vec is what we did here is some sort of wave to vec, right? Sorry, wave to vec, yes. Wave to vec audio for audio extraction. Yes, can you see? Wave to vec feature extract pre-trained. We used the Facebook wave to vec model. You could use any model. Literally, you could use any model that is available to you, but you cannot switch from one model to the other. I need to point this out. Very important, right? Because we have a lot of transformer models out there. Inside a word to vec, for example, we use BERT. It is BERT that knows that 101 is opening sentence and 102 is end of sentence, right? It is going to be different if we use a GPT-2. So OpenAI open sourced their GPT-2 model, right? So if you used a tokenizer from that, these numbers will be different. So you want to stick to a particular network. If you use a particular network to do your feature extraction, you want to use it for all down that you may want to do. You can switch from BERT, change to GPT-2 for the same downstream task, right? That's the point I want to make there. Right, so we have BERT. This is BERT GPT-2. This OpenAI was truly open before they flipped it on us. They were open sourcing their models before they decided to say, you know what, we're close sourcing it. We're not releasing all our stuffs anymore. GPT-3 is still based on the architecture, but now closed. we don't have access to it anymore. GPT-4 as well, we don't have access to it anymore, but it's still based on the same architecture. If you want to check out GPT-2 model from OpenAI, you can come here and take a look. I hope my network is great. Sorry, are we still together? Hope I'm not dropped off.
Yes.
Are we together? Okay, cool.
Yes.
All right. So let's take a look at GPT-2 model. That was okay. So I think this is one GPT-2. Test the whole generation capabilities, transformer Hugging Face here. So this is the paper, the original paper released by the OpenAI team, I think, right? Is a transformer model pre-trained on very large corpus of English data in a self-supervised version. This means that it was pre-trained on, raw text only, blah, blah, blah. You can test out the GPT-2 here, the GPT-2 model, say African Artificial Intelligence Foundation is right. So let's see what it generates next. This was still the early days when they were researching these things. So it's a text generation. So what you're looking at here is called an autoregressive text generation method, right? It looks at the previous words and then looks at, okay, based on what I know that has been written, what is the next word for me to produce? What is the next word? And then it keeps doing that in an autoregressive way, right? Till it finds a 102, right? 102 is end of sentence, right? Until there's a 102 emitted by the transformer model, right? So this is an autoregressive. Most transformers are autoregressive, by the way. Right, so let's go on. So this is a GPT-2 model. I wish they open source their GPT-3 model. That would have been so great, but they flipped their model. All right, let's move on. So these are transformer models. Transformer models are eating up deep learning. Why? Can anyone guess why? Let me see. Maybe there are prices. Should we reach out prices, Dr. Tolu? Can anybody guess? Can anybody just make a guess why transformer models are eating up the traditional deep learning? Any wild guess? Wild guess. Don't be worried that you may not be right. Let's just guess. Any takers? Wow, nobody. Okay. Right. So the transformer model is eating up deep learning for a number of reasons. Number one, for the most part, with deep learning, you can only do the traditional deep learning, you can only do supervised or non-supervised training. But with the transformer model, there is a new method that was made possible, which is this self-supervised. Self-supervised training was made possible, where we can. I would explain that shortly. Let me not bore you with the detail of that right now. Let's move on. Let's move forward for now. Right. So what this allowed us to do was that it allowed bigger scale of models to be possible. There was something I said in the previous class. We are able to do the forward loop using CNN to say that, okay, is this a cat or a dog? Can't we reverse that same process to say that, okay, generate a cat and a dog, right? But those classical methods cannot do that. Those classical methods cannot do that. We can go forward to say that, okay, this is what a dog looks like. The RGB pixel of a 32 by 32 or a 100 by 100 image. If it goes in this way, they will learn the fundamental distribution which is called the latent space. Let's in a technical term, right? The latent space, the features, like, okay, a cat has a what's it called? This hair on the mouth, right? Has a long tail. A dog, I think dogs have shorter tails, right? I don't know, right? They're bigger. They have, the shape of the head is different, right? So it learns those things based on how those pixels are distributed, right? Based on how they are close to each other, based on how different forms of patterns. But can we use that model that can tell us whether it's a cat or a dog to now recreate different versions of cats and dogs based on learned latent spaces, right? Latent space could be, okay, we have a broad category called humans, right? But there are some humans that have big heads, right? There are some humans that have white skin, right? There are some humans with, very giant beards. Even though they are humans, right? It's learning the different attributes and different, ways that human features could be expressed. Human physical features could be expressed, right? So now what these transformer models allowed us to do is now to be able to go forward and backward, whichever way we want, right? In a self-supervised way. You don't have to, essentially say that, okay, label all your data. You don't have to do it in a traditional. It's more scalable to, train models on transformers than on the classical methods. Even though some of them are still built on the classical methods, but it's more scalable essentially. All right. So this was a statement by the state of AI. Is transformers are emerging as a general purpose architecture for ML. So transformers started for words only. This paper, you can get it here if you like reading research papers. My wife would chuckle when she hears this. Yeah. So if you like reading research paper, there's a place called Daily Papers here. Uh, and search for attention. Attention is all you need, I think. Uh, it was from 2017. I could drop link to that. Yeah, this is the paper. Attention is all you need. Attention is all you need. I think there are a bunch of attention is okay. Yeah, here is the paper. Was released by Google researchers. Yeah, June 2017. That's when all these whole attention things started. Whole transformer thing started rather. Yeah, so this is the paper. The methodology, the architectures, and all of that was, properly described here, and that's what gave birth to BERT, BERT. Yeah. So it was transformers was, invented for us to encode words, but we've now been able to successfully apply the same methods for images, for voice, for all other forms of data, and it is producing state of the art results compared to previous approaches, right? So this is kaggle.com, Kaggle survey 2021 says CNN usage down, transformer usage up, right? So I think that's the link to the information right there. All right, so moving forward. So what is this transformer about? Last week we did a bunch of things around. Let me have it open. Transformers. Let me open it. Some things that you could do in transformers. All right, we did image generation. We used Stability AI to do image generation. We used back model. We used back model to okay, where is it? Generative AI demos. Generative AI demo. Yeah. Okay. So we used, um, you know, This model from Facebook, Music Gen Small. Oh, sorry, we didn't do this. I think this must be a new addition to the notebook. Don't worry, we'll try it out later in the class today. We'll try it out later in the class today. So you can possibly generate music using a transformer model, right? You can generate audio, convert audio from text to speech, and do a lot of multimodal stuff. I think we did text to speech. We did text to speech using Bach, right? Also, we did a Facebook MMS model. All these are transformer models. All these are transformer models. I don't think we did this. I think I just added this. That was last week or something. Yeah, we could test run this, what result to generate. And what is this? Okay, so this is a way of okay. Sorry, I'll check out this model. I think I must just be playing out with some new models here. So point is, transformer models is scalable in terms of how it can represent real world. It is not perfect. It's not the best yet, right? It's not like the best it could be, but it's the best we have, right? Right. So let's move on and we'll see why. So yeah, so because they have something called autoencoders. Transformer are natural autoencoders. Um, when we were doing some classification problem, when we're solving some classification problem, using convolutional neural network, or using if you've done NLP at all in any way, right, you will have to develop some approach, right, that has been created. For example, CNN has a lot of layers, that you could add, that helps the model actually learn the representation of the image that you're passing in, right? But instead of going that approach, encoders do instead is to find a way to encode. I don't want to use the word encode again, right? Is to encode. Allow me. Is to encode the information contained in the data set in a way that it contains all the information, or approximately all the information in the original data, such that you can decode it right back to the original data set. So if you feed an autoencoder with an image of a dog or images of dogs, it should be able to extract what makes a dog dog, right? And be able to use another architecture to decode it right back to a dog. So the closely is able to do, the better, essentially, right? So autoencoders consist of encoders and decoders. ChatGPT contains only decoders. By the way, they were able to, you don't have to use both. You could use encoder only. Encoder, if you use encoder only, there are problems that you can solve with it. For example, you could use the encoder module of a transformer model to do text prediction, like on your phone when you're typing. You've typed some things, right? It could predict what you are likely to write next, right? So the encoder part of the transformer module that has been trained on a large data set of words could do that, right? But a decoder, you can use an encoder, for example, to do a translation between English and French. It's a decoder that could do that, right? So you have to combine encoder and decoder together to be able to do translations related problems, solve translation related problems. But what ChatGPT has done, they didn't publish their paper again. We don't know how they did it, but ChatGPT has been able to use a decoder only model to solve most of those problems, do translation, do multimodal stuff, do a lot of things. But most of those approaches are not public, so we don't really know how they did it, right? Because they are not open anymore. So autoencoders allow for self-supervised, unsupervised, and supervised training, right? The self-supervised part is what makes them so interesting because you don't have to, you don't have to train them on heavily labeled data anymore. You don't have to anymore, right? Labeling data, organizing data, structuring data could actually be, it could take you, it could cost you half of an ML budget, right? If you're going to spend $50 million executing on an ML project, 25 million of that could actually go into, organizing your data, structuring your data, and all of that, right? So the self-supervised way allows, transformer models to be able to scale properly over, you know, data sets that are not labeled, essentially. All right, so moving on. So this transformer architecture contains the encoder. Right here in this part is the encoder. This is the encoder. So this diagram that you're looking at, we'll break it down together shortly. It is a transformer architecture for text, for word embedding. It is that the type of, hey, hello, what is this thing? And then it start typing, in response. It's responding to you by, typing what it thinks, right? So you could use the same architecture for audio, for image, just by changing a few components. We'll explain what these components mean, shortly. So an encoder contains word, right? Because you have to inject something into the input of the encoder, right? And what you inject is the word embedding, these numbers that we have here. These are the word embeddings, right? That is what you inject into the That's what you inject into the encoder, right? And the next part is positional encoding. When you say cat eats fish, the cat eats, or the cat ate the fish, and the fish ate the cat. They contain the same words, right? That's 5 words in total, right? The same set of words, but they mean different things simply because of the way those words are arranged, right? So what the Google engineers did, the original author of the Attention is All You Need, is to introduce something called positional encoding. We would explain that as well shortly. So every word in that text input during training is given an encoding. It's also a number. It's also a number. We have already done the text embedding, right? A, B, C, D, apple, dog. We already have the text embedding for that. That's what we're feeding into the model. That's what we're feeding into the model that we're about to train. But now, because the position of those words mean a lot in terms of their interpretation, there is an element of positional embedding, which is the second layer that has been added. Right? Now, the next part is the multi-head attention. So when you say that the cat ate the fish and it enjoyed it a lot. So the eat there, are you referring to the cat or to the fish? It is easy for you, reading to be able to tell that because you're human, right? But how would the machine know that, okay, this is the specific, intent, every word in a sentence? So how this problem was solved in that paper, in this Attention is All You Need paper, is that they introduced an attention head. And I will explain how that works shortly as well. Just, let's stick together here. And then it adds because, what is happening here is that, so for example, this word converts is probably 10463 according to the BERT network, right? 10463. according to the BERT network. Now you've added positional encoding. The positional encoding will spit out some numbers, right? To say that okay, based on how it's arranged, the convert these words to numbers. Convert should have, you know, a let's say, let's do it like this. Uh, so let's say after doing the positional encoding, we get some numbers like 1.2, 1.5, 1.89. What is happening here based on this architecture is that it's adding. Can you see this plus sign? It is adding whatever it gets from the positional encoding to the input embedding. So, or let's say 12, let's say 12, let's say 15, let's say 19. So the original word embedding is 10463, right? But after adding the positional encoding, the new vector representing convert would now be 10463 plus 12. That's where we are until this point, right? So we've added the positional encoding. So every word in that body of text would have its own positional encoding, and it will be added to the input embedding, right? Let me find out if we're still together or we're losing people. Are we together? Is it confusing? Please feel free to stop me anywhere. You see, you may get confused. You will likely get confused, but as I said in the in the beginning, about this class again, and I will add some literatures and some videos that will through over time to be able to understand this. This is the future of machine learning because it allows us to do some things that we were never able to do before. All right. So feel free to stop me if you're confused at any point. All right. Okay, cool. So let's proceed. So based on the transformer architecture for words, now we are not going to go over the rest, right? But if you get the intent, you will understand if you read a new paper about a new transformer architecture because we have a lot of them, right? The transformer for VIT, visual image transformer, is different from this, right? But this is what passed all the GPT, transformers that we have out there, right? But it is the same architecture, encoders and decoders. You have an encoder that is encoding the context, the meaning, the representation odd into numbers. That's what you have at the end of the day, right? And then the decoder that can now use that encoded information to convert it to anything. You can use an encoder that is text with a decoder that is image to image model. You can use an encoder that is audio and decoder that is audio to create a music generation model, AI model, right? You can use an encoder that is image and a decoder that is text to build a model that will tell you what is in a picture. There are a lot of models like that. If we have enough time, we'll get to that, right? You would send it a picture and it will tell you this is a dog lying down on a grass and it is having a ball in its mouth, something like that, right? So it is this architecture that has really led to the breakthrough that we have in artificial intelligence for the past, how many years, right? And that is why, this slide 4 says that transformers are eating deep learning, right? Okay. So the positional encoding, we've added the positional encoding to the input embedding. That's where we are on up until this point. Now the multi-head attention. I will introduce a concept to us on this multi-head attention. Let's go to this file, convert file to numbers. I did something here. All this are encased. Excuse me. Sorry, permit me to put on my camera. I seem to be having a little bit of Um, a little bit of headache. I had to put off the light. Okay. All right. So let's go on. Let me know. Can you see my screen? Can you see my screen?
Yes, yes,
Yes, we can clearly see your screen.
Hello. Can you see my screen?
Yes.
Yes, we can.
yes, we can.
Okay. Cool. Okay. So now we are here. We are here. The multi-head attention. The point of the multi-head attention is to let the model pay attention to the important part of the word or the sentence, the most important part. So how will this happen? I think I have slides that actually cover this shortly. You know what? Let me just go through this slide. I think I have a slide down there that covers this. So, just let's take this as okay. An encoder contains word embedding, positional encoding, and self-attention, and then a residual connection. Right? That's what is contained in the encoder. This is the encoder module. Right now, we now have the decoder module, right, which contains uh, output embedding. It contains output embedding. It contains positional encoding again, also just like the encoder. It contains multi-head attention mask. I will spend some time explaining this. Why multi-head attention mask, right? And then it also now has its own multi-head attention. But the multi-head attention is coming from the encoder. Can you see the line? This line here. The multi-head attention is coming from the encoder. But the multi-head attention mask is coming from the positional encoding, right? And that information is fed through a feed-forward neural network, the regular neural network that we, did in class 3 or class, I don't know, right? To now get, get to a output probability. The output of this decode, if it is a word problem that we're solving, right, would now be a number. It would be a number that we would go and look up in the original text embedding, in the original embedding network. So, for example, if it outputs number 2000, number 2000 represents what? Okay, opening sentence, convert these words to numbers. So 2000, that's numbers. So if this network outputs 2000, right, as the from the decoder layer, what that means is that the output word would be numbers, right? And then African 3616 AI, I don't know how it made AI, one word, but essentially that's what it looks like right here, right? So this is how the encoder decoder structure time to I think I have slides. I just want to separately or be used together depending on the problem that you're trying to solve with them. You have access to the slide after the class, so you can go through them properly. So they're probably properly labeled. Okay. So let's spend some time here. This is the Word2Vec. We use some Word2Vec here. We use some word, yeah. This is Wave2Vec, rather. Okay, so this tokenizer essentially behind the scene is a word-to-vec model, right? What is happening there is that, if let's assume that you train your AI model, your word-to-vec model, on all the English words in a dictionary, right? At the end of the day, if you have a two, I think I have a two, okay, yeah. So this is a two-dimension representation, right? The model will learn, right? Example, this is Dutch to English, right? Or approach means this, or right? But after training the model, it's time representation, right? And this is a three-dimension word-to-vec, right? This is a three-dimension word-to-vec. It will be able to understand that, okay, after the training of the word-to-vec network, that king is related to queen, right? Again, is doing is based on numbers, right? So if this is 0, 0, 0, XYZ, right? These dots on king will have, it will be able to assign a value to king and then assign a value to queen, right? X, Y, Z. So X here could be, let's say, minus 20, Y could be 5, Z could be 2, because it's a positive Z axis, right? This is the dot for king. So imagine it, right? An empty three-dimensional space and a point in that space. That is how it, puts all those words after the word-to-vec, model is trained. So it will understand how those words are used, right? I think from class that we talked about, the way to represent, information using the game of charade, right? All we are doing here is to essentially copy the information of how humans use the language of English and represent it in a numerical form. That is what this word-to-vec is doing, right? So it goes through the way the words have been used according to those large body of text. Could be Bible, it could be dictionary, it could be encyclopedia, all those things, right? And then if you understand the relationship based on the usage of those words, right? So this is an example of how this may look like in a three-dimensional space. There are word-to-vecs that are two-dimensional, right? It just have an X and Y axis, right? And then there are word-to-vec that are 100 dimensions, right? I think the original paper released by the Google guys had up to 100 dimension. Their word-to-vec actually had up to 100 dimension. I need to confirm that, right? But it was hyper-dimensional. But anything beyond 3 dimensions, we can human mind, right? But at the end of the day, it's still vectors, right? It is vector addition, vector subtraction, vector multiplication happening to those numbers, right? And by doing those addition, subtraction, multiplication, it is actually changing the information content within the representation of those numbers, right? An interesting experiment you should probably do would be to, I think we did some, let me see. Okay. Yeah, what I wanted to say is that, every time a right, we want to convert it to action, you'll be able to play the audio. But at the day, this is the data. This is the word array waveform that the AI model generated. This waveform data They are numbers. They are arrays of numbers, which we are converting to audio. Waveform the NumPy. We put the rate sampling and then we convert it to audio, and it sounds like "Hello, my dog is cute," right? Again, you could. This is how it looks for back. Audio array. We have an audio array. This is the input. We say input, hello, clear throat, my dog is cute, right? We pass that into an audio array, and then that audio array is passed into a model. Model will generate, right? It's passed into the model. The model is back model, right?
Boss,
That one that
we can't see your screen, sir.
talk like a female,
We can't see your
male,
screen.
and all those things, right? And at the end of the day, what we have is an audio array that represents a spoken word. So those audio arrays, you could manipulate them and change them and transform them and do whatever it is to them, and it change the way the words will sound. So what I'm trying to establish here is that all those data forms that we represent, that we relate to in reality, can be, reduced to numbers, and now we can bring them back from numbers. Oh, sorry. I just realized I'm not sharing my screen. Shared. Sorry to hear that. Oh, so sorry. That was a long time ago.
Not too long, sir.
Thanks, Dr. Latini. Track a bit, right? So I was trying to establish the fact that the word embedding or audio or image embedding, whatever embedding it is a dense representation of the information contained in the dataset itself. And whether it is us converting the word embedding to something else, or we are converting, we're trying to convert the, what embeddings to the original data, we can, by manipulating the arrays, we could actually change that in particulars. And this is the, one of the reasons why, the advocate of, AI being too dangerous and all that. This is where they come in, right? We could create an if President Tinubu that he didn't say in reality. We would just sit down here, we would write those codes, and then we, do everything, and we could instigate violence, we could do all those things, right? Because at the end of the day, all those things are just vector embeddings that could be artificially created and then compiled to look like original data. To a human observer, you would never be able to tell the difference if you have a good compute and you do the job well, right? So this is the power of artificial intelligence. Now, where we're headed to is a point where we can now build a classification model that can tell whether this is artificially generated or it's actually a real image, right? That's a very interesting research area. But let's go on our adventure of our transformer model, dissecting a transformer model. So this Word2Vec is what we feed in here. That's what we feed in here. The Word2Vec input for word transformers, for word-based transformers, right? Again, transformers has been used for images or for audio, for things, right? For anything, as a matter of fact, right? So that's we get the textual representation of that word, we feed it in, we add the positional encoding, we feed it in, we now do something called the multi-head attention. And how this works, earlier we used an example. The example was, the cat ate the fish, right? So, okay, the cat ate the fish, and the fish enjoyed it so much, right? Let's do this. Let me put up my notepad. That's my notepad not opening. Okay. Sorry. Okay. So this is the word, right? The cat ate the fish and it had so much fun doing so. For the multi-head attention, what happens is that it will look for similarities of these words between itself and between every word in that sentence based on the word to vec network that is used. Right? You know what I was looking for here. Okay. Cool. Right? So we're at multi-head attention now. So it is trying, the goal of this guy is to pay attention to critical part of the sentence, to highlight it much more than other part of the sentence that is not as important, right? As you can see, we are building these layers in a way that is you can relate to why it is important, right? Because in a word, if you say that, okay, the cat ate the fish and it enjoyed it so much. This eat represents the cat, right? But why not the fish? Why not the fish? You could tell, I mean, because you studied English for a bit in school, right? But how can we make it easy for an AI model to, pay attention to key part of words like this? So what the approach that was used to solve this problem is called cosine similarity. Cosine similarity. And here we have a problem. You still have access to all these things. It's in the GitHub, right? You can play with them after the class. So we use the same network, right? The same BET network, pre-trained network, right? We loaded it. We loaded the tokenizer from the network, right? We loaded the tokenizer from the network, and then we put these three texts: input word 1, input word 2, input word 3. Convert these words to numbers. African AI Foundation is creating an army of AI champions. Convert these words to numbers. African AI. Let's change this a bit. The African artificial let me see. I need to change it in a way that it will kind of like match. African AI Foundation. Okay, yes, awesome. They are different actually, right? The first one says African AI Foundation is creating an army of AI champions. The next one says African AI Foundation has created, not is creating, has created an army of AI champions. And the third word, unrelated, right? It says the African economy needs to grow for it to become very competitive like European economy, right? We have these three sentences. We want to do a short exercise, right? We loaded our tokenizer from here, right? Auto tokenizer from pre-trained model, the BET model. Uncased, by the way, means that it is not case sensitive, right? It is not case sensitive. So there is a BET model that is case sensitive. It will understand African differently from A, from small letter A with Africa, right? So there are a lot of a variation of BET model, but this particular one that we're using is, not case sensitive. It's the uncased one. So now we loaded our tokenizer from here, and then injected the input word 1, input word 2, input word 3. Our tensor is PyTorch, and let's run this. Sorry, let me install my transformer real quick. We may extend the class a little bit more than 2 hours. Let's pardon ourselves for that because we didn't have this class last week, right? I want us to touch on diffusers as well. Okay, so this is installing. We're pip install transformers. We're installing transformers. Be fast. Okay, I think I can. Okay. So I'm importing all these modules, so I could use them for the experiment on cosine similarity that I want to do. All right, so I will run this. Okay. Tokens 1, rather. Tokens 1. Okay. So all right. Tokens 1, tokens 2, and tokens 3. So let's take a look at what those numbers look like. So this is token 1. It looks so much like 2, right? These are the word embedding from the first sentence, right? The word embeddings from the second sentence, and then the third, right? So what we want to check is the similarity between all these words. You could tell that word 1 and word 2, sentence 1, sentence 1 and sentence 2 are so similar. You don't need an angel to tell you that, right? It's just, we're simply just, saying that, okay, foundation is creating and as created. That's just the difference. But the third word is saying something totally different. It's talking about something totally different, right? So we want to check for similarity. To do this, is a cosine similarity is essentially a dot product of vectors. It's essentially just a dot product of vectors. Think of these. I don't want this to be so technical, but you will have to go through this over and over again to be able to, to fully grasp this thing, right? This is a three-dimensional space. It has X, Y, and Z part of the vector, right? For the word coin. And if we want to find the similarity between the word coin and the word man, right? So it is going, the mathematical function is essentially going to do a dot product between the two vectors. That is the approach that was also used in this attention is all you need paper right here, So if your dot product is big, that means they're similar. The bigger they are, the more similar they are. Where am I? Okay, yeah. The bigger they are, the more similar they are, right? So what I did here is to say, okay, this is the tensor for word 1, for word 2, for word 3, right? We're essentially just, put in the word 1 and word 2 dot product of, the embedding for word 1 and then the embedding for word 2. I could remove this, but essentially we're scaling it by the size of those vector numbers, right? So that everything will amount to 1, But this is essentially the dot product. But what we're doing here, the reason why we're dividing it by this number is so that, it could be properly scaled and, the difference could be, better observed. This approach also was used in the attention is all you need paper that the Google guys created. So when we did the, token 1 and token 2, right? We are comparing the similarity between the words in the embeddings between the token 1 and token 2. We got 0.96, right? Let's see, 0.962. And when we did it between, the sentence 2 and sentence 3, we got 0.66, right? That means this, what is essentially telling us is that the similarity between tokens 1 and tokens 2 is higher than the similarity between token 2 and token 3. Sorry, sentence 2 and sentence 3. Oh, of course, a sentence is a bunch of tokens. So yeah, I hope you understand, right? So this is what happens in the attention layer of a transformer model. Right here. This is what happens in the attention layer. So what happens is that the dot product that you saw there is what is done for every word. So there will be a dot product between a D and D itself. Of course, that will be very, very high, So let's say it's 1. The dot product between 1 and 1. The dot product between D and cat, right? The embedding, of course, the embedding of those number, right? So let's say this is 0.3. The dot product between D and et, 0.2, right? The dot product between D and D, of course, and maybe another 1. The dot product between D and fish, let's say 0.9. And then the dot product between D, we are still on D, right? The first word. We are doing the dot product between D and every other word in the sentence. So that's how we're going to do that. And then we will come back, do the dot products between cat and D, right? The dot product between cat and cat, the dot product between cat and et, the dot product between cat and the cover till we complete that for all of the word in the sentence. What you will find is that the words that need the most attention to be paid to will have higher numbers because of that similarity function than the words that are not. Are we still together?
Yes.
Okay.
Yes, we are following.
Thank you. If you get confused, don't worry, don't fear, don't scare. It's a very, very advanced concept, and even the top folks in the field get confused often, right? We are explaining the attention layer, right? We've talked about the input embedding, we've talked about the positional encoding. We've not really explained the positional. I'll explain that shortly. Do we have enough time for this? Good. Okay, positional encoding. We add the positional encoding number to the input embedding, and we now generate the multi-head attention between all the words in the sentence, right? That is to be encoded, right? That attention is essentially doing, for example, this is 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So we would have multi-head attention of 13 variations. The first one will be the word D to the other words. D attention here is that it's checking the similarity between D and the other words. Here, it will be checking the attention on cats with the other words. Here, it will be checking et. Cosine similarity function, the same thing that we did here, right? Cosine similarity function between where's my note? Between et and the other word. So, but if once it's a grunt exercise to do manually, but what you find, and this is the point of doing all this research, look for the pattern that could help them build this architecture that would scale, right? So what they found was that the cosine similarity number for the words that are the most important to the actual word that we are looking for is higher. So in the case of et, right? Et with the other word, the cosine similarity for fish will be higher because it didn't eat the cat. It didn't eat the cat. In this word, the cat ate the fish. Right? And the cosine similarity the dot product for it on the it on fish will also be higher than it on cats. So that is how it will know that, okay, it is fish that it represents, that it's not cats. Keep going on and on and on. So it helps, this structure helps it to be able to focus on some parts of the word and be able to do connection, inference, contextual meaning. This is contextual. Okay, I think I put it here. Cosine similarity search between tokens 1 and tokens 2. Higher number means very similar, right? Higher number means very, very similar. So the guy, remember, the guy was trained on large corpus of text. So it knows how words have been used. So it understands how, what those sense in English language. It knows those things, right? So now, when he's doing the cosine similarity, against that, the words that are closely matching will have higher number than the words that are not, right? So that is how attention in transformer models is solved. So multi-head attention, right? For each of the word, multi-head attention. So now, what this next layer is, it's adding a normalization layer. At this point, what you would have is something like, query key value. Query. This is the query. Where's my note again? So when we are on the first word, we are looking for the similarity between D and cat, D and et, D and D, D and fish, D and eat, D and and so forth, right? So D is the query. All these other words are the key, right? And that's how that is what it will use to now get the attention value, right? For that step. So the end of the attention layer is have a bunch of matrices, on query key value, and those values represent the words that you should pay more attention to in the body of text. And then that is fed to a feed-forward neural network. That's a regular neural network class, 2 or 3, I can't recall precisely, right? So look at this arrow. After we have generated our value from the multi-head attention, we now add the words, the embeddings that we've added positional encoding to this arrow here. So, for example, I think where did we put that? Hold on. I think that is here. So here we said, if convert, original word embedding for convert is 10463, right? And then positional encoding for convert is 12. After adding both together, we get 104 what? 10475, right? 10475, right? So that is what we have at this point. That 10475 is now added to the attention head. That is what you're seeing here. That is added to the attention head, and then we have a new bunch of numbers again, right? And those are the numbers that are now fed into the feed-forward neural network. So all the weight in the encoder is here. We established that a neural network model is essentially a bunch of numbers that encodes the pattern between the cause and effect. That's connecting two independent variables, right? So those numbers from the normalized stuff is what we now feed into the neural network, do the normalization again, and then we have our encoder numbers. With these encoder numbers, you can solve a lot of problems already as it is without adding the decoder. You can solve a lot of problems like, let's even ask ChatGPT, let's ask ChatGPT. What are the use cases of an encoder only transformer model? Okay, can you see? Name recognition, text summarization, document retrieval, similarity matching. Machine translation. You need a decoder mostly for the machine translation. I don't believe this much, right? Or language modeling, of course. Dialogue system. You will need a decoder for this. Speech recognition, yes, right? These are some of the use cases of an encoder only part. So the fact that you have an encoder alone, you have something of value, because what you have here, the output of the encoder, dense information compressed and just expressed in numbers. So those numbers are a representation of every information that is contained in the input word. All these layers and meandering and massaging of the numbers that we have been doing is so that the output of the encoder can be as rich and as representative of the input as much as possible. You can understand and relate that if we remove the positional encoding, it will know that those words are there, but it will know how, in what order they are used and what inference or what meaning it has based on those order, right? So this is very important. The attention head is very, very important also, so that you could pay attention to significant part of the of the words. This is so similar to the LSTM. We didn't touch LSTM because it's kind of like it's phased out now with the transformer model. There's no point going there. We did convolutional neural network because it's still relevant even in diffusion models, right? So now we fed out to the feed-forward neural network, and then we get some numerical representation. The numerical representation is the same information as the input, just in numerical form. Right. The encoder module of a transformer architecture. Now, let's move to the decoder part. The decoder part is this, right? So the decoder part takes in input, output embedding. For all transformer models that are word-based, that are solving word problem, the first token that they use is 102. If it is BERT, is 102. That is end of sentence. Some people use 101, start of sentence. It doesn't really destroy the performance or anything, right? But you need to seed the system, right, for it to start predicting what the next word is. You need to start from somewhere. So the first word output embedding that you are injecting is either the 102 or 101 if it is BERT based, or whatever it is, end of sentence, EOS, right, or start of sentence, SOS, right, whatever that signify in of the word to vec model you're using, right? That is fed in. Also, you add in the positional encoding. Now you add in the maxed multi-head attention. The difference between multi-head attention and maxed multi-head attention is this, right? This, when we did the attention, multi-head attention, we were checking the cats, similarity of cats between the similarity of the word cats and let me drink water small. Okay. So for the first word, right, we're checking the similarity of D and cat, D and X, D and D, D and fish, and D and all of that. So for a multi-head attention, it can see all the words. It can see all the words in the text. But at a decoder, because the decoder is not, it is trying to generate output words, right? So if the first word is end of sentence, right? Whatever it is, EOS, end of sentence. right? This end of sentence, almost all, word-to-vec models have their own representation in, numerical form, right? So if you're seeding the decoder model with end of sentence, you add your positional encoding number, right? You add it, let's say the end of sentence, let's still stay with birds, right? 102. And then we add the positional encoding, let's say it's 15. So 102 plus 15, that's 107, right? Now, at this point, we now have a multi-head, maxed multi-head attention. Instead of us doing all the, similarities, right, with all the words, we only do similarities with all the words that have been decoded. And we mask anything that, like, you cannot see. So in this case, at the decoder, it is only going to be doing the similarity of EOS to EOS. Right? Excuse me. So let's say, let's use this ChatGPT response as an example, right? So the ChatGPT developers would have, at the end of these things, let's assume they use a decoder, encoder-decoder architecture. We all understand now that they use decoder only, but let's assume they use encoder-decoder. So they've generated the encodings for these words, right? So now to start the decoding process, which will generate this text, the first thing they will send to the decoder is the EOS, right? So the encodings for these words is available. The information of those encoding is available here. Right? That is the multi-head attention. That's where it's being injected in the decoder, right? So the EOS is sent into the output embedding. We get the positional encoding for that, and then we do EOS similarity, cosine similarity of EOS to EOS. Whatever we get is now part of the multi-head attention. So this is multi-head attention. Similarly is how we do it with this layer of the decoder as well. Everything remains the same. Decoder layer, the feed forward, the normalization, linear softmax, and then output probability. Right? I don't want to. I would attach a link that will allow you to spend more time here. I don't want us to spend so much time because we need to get into Diffuser shortly as well. But what is happening at the end of the day is that at the first word, this guy will generate an, right? The first word in the decoder will generate an encoder only transformer model, right? So an will have, an. So this is the first word. Remember, it's autoregressive, right? So the next word will be this. And let's see. Encoder only, okay. Encoder, no. Encoder only. For the sake of simplicity, let's just put it as one word, right? Only transformer model. Right. Encoder only transformer, and then on and on, right? So at this point, the maxed attention will generate, the first one is EOS alone, right? That's the starting point for the decoder to start generating text, right? That's the first seed input, right? So it generates, based on the, encoder embeddings, it generates the first word. Now the maxed attention for the next one will now be against EOS and AN. The next max attention would be EOS and encoding, and on EOS and encoding only on EOS and AN. And then it keeps going on and on and on and on, right? So max attention disregards the fact that, there may be text here. There may be text here. So it only, if there are text there, kind of like max them. such that it could, keep building the text in an autoregressive way, predicting the next word, and then before you know it, you have something holistic as this. So this is how transformer is solved. I jumped off a lot of details, like the softmax layer. There's a softmax in this multi-head attention, because at the end of the day, what we're doing is that the query key value, we are scaling them. I jumped on those details. They're not as important, but if you understand this fundamental structure, you will be able to tweak any transformer model to your own liking. There's a transformer model that you will send an image, and then it will tell you the description of what is going on in the image. A transformer model that you will send in a text, it will generate an audio. You will send it an audio, it will generate a text. You will send in a text, it will generate an image. You will send it this is how it is accomplished, right? For some of those multimodal models, some of the layers are a little bit different, right? Especially around the image generation decoders, right? This is only text. This is text only. Text encoding, text decoding, right? So this is the structure of the transformer model, and this has scaled so well. Now, for an image-based transformer model, the input would be, who can guess what the input would be? For an image-based transformer model, what would be the inputs? For word, chase numbers. The pixel information, right? Fantastic. For an audio-based transformer model, it will be based on there are a bunch of ways, but essentially the frequency information, right? At the end of the day, the frequency information. Fantastic. Thank you so much, Ayomide. So similar things that we've done in the past, but just flipped on its head. The beauty of this autoencoder, so you don't have to, do so much work labeling, and it will find the representation of the data. It can learn the latent representation of the data, and now be able to do a lot of interesting things between the decoder and the encoder layer, right? So this is how it works. Can I get to speak about this encoder positional encoding? There are a lot of ways to do positional encoding, right? There are a lot of ways to do positional encoding, but the approach that was used by the Google guys was a sine cosine wave. That was the approach that was used, a sine cosine wave. So you have a sine, you have a sine here. I think this image must have been cropped, right? Sine wave starts from 0, right? A cosine wave will start from, like from the right on top here. Yeah. So this is the formula they used. Position is the position of the 1002i. I is the ith number of that word divided by the model. What is the size? What is the word? Token. Token limits, right? GPT-4 can take 1024 token limits, right? So for a ChatGPT-4, this D model is 1024, right? This I is the ith number, because you have to do the positional encoding for, so for example, cat eats fish. Cat is the word itself, right? The position 1. So you would find the positional encoding for cats, with eat, cat with fish. Fish eats cat, right? Maybe a shark, right? Maybe the cat. You find a positional encoding of fish in relation to it, and then in relation to cat. So I is represents the the word that you are doing that in relation to, but the position is the very word that you're finding the position encoding. At the end of the day, this will output a number, right? This formula will output a number 1.7, 1.2, 1.4, which represents the order, the position of that particular word in the order. As the word keeps going, what you will find is that words at the tail end of the sentence, the frequency will be bigger because of this formula. So you will have a very, very, very low likelihood that the positional encoding would clash, right? That likelihood will be slim. It's not impossible, but even though when it happens, it's not going to cause any problem because it's a matrix. Matrix of the actual word with the other words in the sentence. You're doing the positional encoding of the actual word, just like we did for the cat's head fish. Positional encoding as well works, right? So similarly, this is what is done across other modals, modalities, text, images, and okay, yeah, this is how it looks like exactly, right? So for the first word, so positional encoding for the first word is 1.0, right? This is cat. Cat eats fish, right? Cat eats fish. So for you to get the positional encoding for the next word, you can keep adjusting this I. Let's see, position. The position would be one word divided by 2000 raised to power 2i, right? Divided by D model. So D model, depending on the context length of the model you're trying to build, it is your choice. This is your choice, right? ChatGPT, when it was first released, it had 512. That means the words that you are, if this is more than 512 words, it won't be able to understand it, right? It can only understand maximum of 512 words. That's what that means. So it can generate positional encoding for up to 512 words. So that's the representation of this D model. So this is the formula that was used in the original attention is all you need, right? Okay, so this is how the attention, stuff works. D with D, D with pizza, D with came, D with out, and that's how you get a self-attention. And yet it generates a number. The higher the number, the more attention it places on those words, right? Right. So I explained the query key value. The query is the actual word. The key is the word that is the similarity dot product is done against, and then the value is the scaled softmax of the two. Phew. I've confused a whole lot of people today. How is it? Who is lost? I can see LOL. Quite overwhelming, but still, yeah. So see, this architecture, a lot of people are creating new transformer architecture every day, right? But the thing there is that don't dwell on the details of what those Google guys did. The ChatGPT guys, the OpenAI guys have changed it up. Of course, the Google guys revealed to everybody that there's a new approach out there that we can use to do our training, and it can give us better outcome, right? Novel results. That's what the Google guys showed, right? But the OpenAI guys have already changed almost all these components. They've changed almost all these components. But the fact is that, if you come here, Hugging Face, you will see a lot of transformer architecture that has been created so far. I'm not logged in. Okay, I think I'm in the wrong place. All right. So if you come here, come to okay. So for example, now, if you come to task, these are all the tasks that transformer to be able to solve, right? These are all the tasks. So you can easily say that, okay, let's see, it's a simpler one. Hugging Face started as a transformer promoter originally before they diverted into other things. Let's do image classification, right? So you just say simple from transformer import pipeline. This is the task that you want to do. Image classification, right? And then you call you put the part of the picture. You remember the whole classification that we did? Is it a cat or a dog or anything? This is all the code that you need to do it in transformer model. This is all the code that you need to run to do the same thing with transformer, right? Just import the pipeline. They've built out all those rails in a repeatable way from transformer import pipeline, from this pipeline that you imported, passing the image classification, right? And then passing the path to the image. It will tell you what kind of animal it is with a percentage score of certainty. That's an example. And that is why, in that image, you say transformer is eating up deep learning. Let's look at another quick example. Image to image, right? Image to image. I think we've not done something like this. Have you guys seen those apps that will ask you to upload, pictures that are blurry? If you have a very bad camera, upload those pictures. They will help you upscale them, help you do all those things, right? Who has seen anything like that before? Has anyone seen something like that? Right? Image to image. Those are image to image models, right? You essentially so that's using diffusers, right? Diffuser is a form of transformer. It's using the same encoder decoder structure, right? You pass in the model, and then you say that you pass in the image. This is an image to image, right? This is an image to image, and then the prompt is a fantasy landscape trending art station. So whatever it is there, it will now augment the image that's already there in this mountain image, right? And then add this fantasy landscape to it, and add the trending art station to it as well, right? So you have a image of a mountain, and then it is adding whatever it is that you want to it. And then you can save the image and as fantasy landscape and visualize it if you want. So to see all those models that are available, you can come here. You can come here and type the models, but there's a place that I want to show you. Okay, docs. Fantastic. I missed that. So transformer and diffusers, right? Just don't worry about the rest. Transformer and diffusers are the things that we wanted to touch on today. We didn't really touch on diffusers much. So transformers, if you get in there, you will see okay. All right, fantastic. See, these are some of their novel models, text models. Albert, BART, BERT. This is the one that we used to do the tokenization, right? This is the one that we used to do the tokenization for Word2Vec, and they have for a whole lot of other models, right? So this is word-based. This is using the structure that we described in this class today. That transformer architecture that we described in the class today, that's what this is using. But now there are vision models, transformer vision models as well, right? VIT, DPT, a whole lot, REST, a whole lot. Also using the same architecture that we described today. Each of these models are changing some of these components, and then they usually link the paper. Albert's model was proposed by Albert Elitebert for self-supervised learning of language representation. So if you want to read the paper, you just come in here. The actual researcher that found the method, right? If you're interested in that, you can read the paper that led to the creation of the model, right? So these are lot of interesting, architectures. This is a ConvNet for the 2020s, right? You can click here to read the paper if you're interested. I think I might have closed it. Okay, cool. Right. So this they explained what is where how the stuff is structured and how it generates what it needs to generate and all that, right? But at the end of the day, it is going to be as similar as possible with what we have. The changes would not be dramatic. At the end of the day, it is transformation of input data to an encoded number that closely approximately represents that input data as much as possible, and then having a decoder that can convert that back to the data if that's what you want, or do some other interesting multimodal problems. So this is a visual recognition problem, right? To use it, they have a sample code and an example to use it. So this is transformer in a nutshell. So we can exhaust it. I try to as much as possible to collapse this into one class, but unfortunately, it's kind of right. These are audio models. These are audio transformers. Using audio wave input and then doing whatever they need to do. So, for example, this is generating music. This is converting a pop to piano. This is what else? Speech to text, VITX, wave to VEC, wave to VEC conformer. So if you're curious about what the approach is, how it's converting the input tensor or input data to or maybe it's an encoder only or decoder only, you could get that information from this page on their docs, right? So all the transformer models ever built to solve a specific problem has been added here, right? So you have some multimodal, and then you have some reinforcement learning and time series model and all of those kind of things, right? So in order for you not to get lost in the world of transformer, in order not to get lost, the best would be to pick a problem set, right? Pick a problem set that you would like to solve and find out if there is a transformer pipeline that has been built for it. What a transformer pipeline is essentially doing is that all those rails, all those, addition, vector, addition, adding position encoding, adding multi-head attention, adding, feed forward network, all those things that you would have to do, that's what has been done into that pipeline. So once you invoke the pipeline, you would be able to utilize, once you invoke the pipeline, let's go to task again. Task. Text to speech. Yeah, let's do a text to speech, right? For a text to speech, you are pipeline text to speech, and then you're passing the model that you want back. This is the back that we played with last week, right? Last lesson, right? So you say, okay, the pipeline that I want is text to speech. So it will do the whole, layer that is, that works with back all the transformer layers, the input embedding, the, how the data needs to be, and all those things, the encoder, the decoder, and all those nonsense, right? I did hard work of explaining these things so that you will appreciate what this thing is doing for you, right? This guy is helping you accomplish all those things that we just explained over the past 2 hours, right? And then you can just pass the model that has been built on that pipeline, and then you can accomplish your downline task. Now, this is saying synthesizer because you injected synthesizer here, and then you're simply saying that synthesize this word into an audio. What it will do is that it will generate a number array, and then that number array, you will convert it to audio, and then it will speak it as though this is it. How are we looking? How are we doing?
Fine.
Okay. See, senior man. Let's see here from Deborah. Deborah, are you lost? June.
Why? This is so overwhelming.
Joy. Yes. I didn't realize. Wow, incredible. No worries. So it's next class, next cohort is starting very soon. Next cohort is starting very soon, and yeah. Don't worry. The transformer architecture is this architecture that I described today is the original 2017 novel architecture. A lot of people, if you read these papers that I introduced you to, a lot of people have changed it, and they will tell you why they changed it is so that they could, be able to, accomplish these things, so that you can capture this much information, so that the information density can be increased a bit, so that So a lot of people have changed it. Unfortunately, OpenAI is not contributing their research anymore. So we're kind of like blindsided here. Everybody knows that their approach is kind of like superior, but we don't know what they're doing. But we have a whole lot of interesting things that you could do with this text to speech. You can do a customer support machine learning app. You didn't build jack shit. You just use a transformer model, from back, and then pass in the task. This is the task. Pipeline takes a task. The first parameter is the task. If you don't pass the second parameter, best model that fit the task, right? If you don't pass the model parameter, it will find the best model that fits the task. But if you pass the model, it will use that specific one, right? Let's take a look at more examples, right? Video classification, right? This one has more, you have a path to the video, you have let's see what model was used. VAE video MAE for video classification. If you check their documentation, you will find that that paper, that original paper, and the scientists that wrote those discovery in terms of how video can be classified, right? So this, you pass in a video like this, and it comes out, say, playing guitar, with 0.5 score, playing tennis with 0.1 score, cooking 0.0. I don't know how this symbolizes cooking, right? So from image to explaining what is in the image. Sorry, from video rather to explaining what is in the video, right? We've never been able to do something like this before Transformer came through, right? So don't worry, it's gonna take a little bit of time for you to get a hang of all the layers involved in Transformer, and those layers are so dynamic depending on the task, right? So because you can easily get lost in the world of transformers because of that all the research papers that have been getting released in the past how many years has been all transformer, mostly have been transformer based stuff that almost no one can keep up with the advances, right? So don't worry, just understand the nuances, right? Okay, we are feeding information in, we are that captures the representation of that information. Now we can now use the decoder to now recreate a variation of that input. That's the whole thing that is happening, right? The detail of the layer will change depending on the task that it needs to solve at the end of the day. Yeah, awesome. Yeah, so I will send the class notes and attach some other videos that will help you. I passed on a lot of bits of time on the original architecture that the Google guys created, the original Google architecture that they released in 2017, right? Those details are not earth-shattering, but those videos will help you understand it better. You will have to possibly even watch those videos multiple times to get a good, and if you care about the mathematics of how those things are happening, you see, we are adding positional encoding to input vector. We are generating the similarity of all those words to see how they relate to each other. We are now, adding the output of the positional encoding to the normalized, feed forward neural network. right? And that's how we generate the encoding. So some of those details will change depending on the transformer architecture you're using and depending on the task that you have, right? So the belief is that everybody believes that transformer is here to stay. The approach is stable and is repeatable, and this is why this image is like this, right? So we have software eating the world, we have deep learning eating software, and then now we have transformer eating deep learning. This is a very, very, very fresh and out of the oven kind of technology. So don't be worried that you're not catching up. Just if you're interested in the specific details, documentation page on Hugging Face, they'll always link the scientists that discover that approach and then explanation on how it works. So go to the docs page, if you want the details, but go to the task page if you want the application, right? So the coming hackathon that will happen, we want to see a lot of people leveraging transformer models. Just come to the task. What task do you want to do? Okay, I want to build a telecommunication product that will work for something, whatever it is, right? And then just pick up the task, use your transformer model, punch in your data, and then demo it, and then possibly you'll be the winner, right? Or if you have some classical approach that are non-transformer based that works, you're welcome to use that as well. But just wow the judges. Yes, that is transformer in a nutshell. See, my deck contains something about diffusion, but I don't think we have enough time to cover that. We've really spent a lot of time. I touched on this last week. If I may just explain it, here is the unit. Instead of the decoder, the encoder decoder structure for the transformer, the diffuser uses unit. This is encoder decoder for unit. It's for image generation or video generation and all those things, right? Encoder decoder, right? It's encoding the representation in the image, right? By adding noise to it. We touched on this last week. By adding noise to it, and after adding those noise, it will then try to recreate the original image, right? All those times it will be calculating the probability of how much noise it needs to remove, right? This is the noisiest image. This is the noisiest image, right? This is how much, what is it, calculate how much noise that needs to be removed, and then get a better upsampled image. Calculate how much noise needs to be removed, get a better upsample, it gets the right image, right? Let's close this class by 7:30 Nigerian time. Let me just show you a quick demo on diffusers. I hope it's not. It's been added to the Google GitHub, right? So this is the transformer model. Sorry, this is the diffusion model, right? Let me just run it. You can just, for you to play with it, you can just run this. All this code has been added, and you should be able to easily test them. I just want to show you the process of noise generation and noise removal. That's all I want to show you here. Next week, I will show you how to. Oh shit! No, I think, did I not save it? Sorry. Open DDPM. I think. Oh. No. Something terrible has happened to this notebook. I thought I saved it. No. Okay. I guess we can check this out some other time. I wanted to show you, adding noise to an original image and then the process of removing noise from the image so that we can see, how when you type in your Midjourney is no longer free, or into your DALL-E, generate an image and this and that, how that process works. That's what I wanted to show, but I think I might have scattered this notebook. I might have scattered the notebook. Okay, you know what? Let's move that to next week. Let's move that to, go through that. So this is an interesting notebook. You can play with this. Transformer can do anything, do a lot of, multimodal interesting stuff. You can check it out as well. Let me see. Do we have, okay, I think we went through this the other time. We went through these notebooks the other time. Yeah, we went through this once. Yeah. Okay, so next week, what we would do is that we'll just, close up on diffusion model, with code, using code, diffusion model with code. We've already done most of all these, how to use all these models with code from last week. That's what the intro was about. We did an experiment with, text to all these things. That's what we did, right? But now today, we now understand much details. We went deeper into what is going on within those models, right? And yeah, that's how those generative AIs are generated. It's mostly transformer models that's behind them. Ngozi, are you raising? Okay, I can see signs like 2 here. All right. Yeah, so we went through the process of using generative AI models. We generated voice from text. We did all of those fancy things, right? But today we went deeper into the transformer model that is powering all these things, right? We narrowed down on the word to word, right? Transformer model, but there are a bunch of other transformer models, words to anything at all, right? Just play with the task part on Hugging Face Hub, right? Use the pipeline method once you import that you can import from transformer, and you can almost accomplish anything. Almost all those tasks, you don't need to reinvent them, right? Because it is from one thing to one thing, right? Those pipeline have been built for you. Just leverage them. If you have your own model, you can pass it as the second parameter. If you have a model that is publicly available, you can pass it as well. Or if you don't know which is best, just leave it empty. The transformer model is going to find the best model that is open that can be used for that generative model task, right? And yeah, that's it. So next week we would go on diffusion in detail, from codes, how to train a diffusion model, how to let's visualize the process of adding noise to an image and then the process of denoising the image, right? DDPM means diffusion, denoising diffusion probabilistic model, right? That's what it means, DDPM. And that's one of a way of adding noise to the image. It will look like a blurry. We will now get the model to now get the image right back to the original. And then once it can do that efficiently, then you have a model that works. And from there, it will be able to generate almost on things that you're not trained on. Yeah, let's get into questions. I took so much time today. It's just that the class today is kind of like quite thick. Okay, Steven says, I thought CNN and NLP are end all and be all, not knowing I just play chai. Well, you are not playing. All those things are very, very important. You wouldn't understand this. You would stand no chance at understanding transformers if you don't understand those ones, right? If the notebook for diffusion worked, I would have, showed us that everything that you did in CNN, we still used it in diffusion model, right? We would still use all those things, all those convolutional layers in adding noise and in denoising those images, right? So that you understand the convolutional neural network affords you the opportunity to even, understand, transformers. So they are not a waste in any way, shape, or form. Hi, Israel. The previous class audio was very bad and I could barely hear. Wow. So sorry about that. Wow. Wow. I didn't know that. Oh. Is that the same experience that you got, Steven? The audio was so bad. I think you played it at the American Corner last Wednesday. Wow, so sorry, June. I don't know how we can, correct that. Questions. We have 10 more minutes. Ask stupid questions. Okay, let's reward people. Someone with the most stupid question. Okay, June, you may want to check your internet. I think Stephen was able to catch up with the audio without any problem. Let's ask stupid questions. What's confusing us? See, everything that you are seeing on ChatGPT, June, is all magic of transformers. This, let me show you something that ChatGPT added. Oh, so sorry, Stephen. Okay, they added a feature to translate a code to translate an image to a code. Did I get that right? I think something like that, right? That was last month or last week. Yeah. Let's see. Those guys are stealing from open researches. They are stealing from scientists that are publishing their research, but they are not opening their own research anymore, right? They are thieves. That research was from a guy. Okay, let's check it out. But yeah, point out where I was going to answer your question, Mr. June, is that yes, we are going to get there, but the way there is to help to have specialized models that can solve one domain problem, right? The way it's going, the way we're going, right? We're going to get there someday where you will simply tell the AI to do something and it will find the optimal tool to do it, right? Dr. Tulu knows that there are some products we are working on in the lab that is doing this already, right? You can ask it, hey, there's this product we're deploying for one company. You can ask it, hey, what is, give me this information about my company, and then it will, look for the best way to provide that answer for you, using all the tools that it has. So the simple answer to that is that yes, it's gonna get there. What you're speaking about is an AGI that can accomplish any task without you having to explicitly, build a pipeline or build the modal, the modality, right? But the journey there is to build specialized modalities, ones that can solve text properly, ones that can solve images properly, ones that can solve audio properly, right? And then by cross-referencing across those modalities, you would have a more mature, AI. But to say that build anything from where we are today, that would be a long shot. But yes, we are on our way there. That is an AGI right there. That's an AGI you're speaking about. Will you say transformer plus deep learning equals to generative AI? See, Transformer is still using deep learning. I will call Transformer deep learning 2.0. Transformer is essentially deep learning 2.0. So, transformers, you can use it to do almost any task, including the things that you could do with classical AIs, like classification, task. I just showed you a code to use transformer model to do image classification, right? On a pre-trained model, of course, right? Just in 5 lines, you'll be able to say what is inside that stuff, right? Okay. Next week, I will demo something to us. We will produce an image so that it won't look like it's me that I've coded the image up, right? You guys will give me a link to an image, right? And we will have a transformer model explain what is happening in that image, right? So things like that. Let's leave it till next week. So it is not essentially generative AI only, but yes, it is transformer model that enables the possibility for generative AI. Without transformer models and the autoencoder features that it has, we would never be able to accomplish, an AI, converting data sets and working its way backward. What we did so far before the generative AI is working forward, right? We'll tell whether the word text is positive or not, text classification, whether the image is one thing or the other, right? But now we are working our way backwards, to the original data that we started from. So without transformer models, would have never been able to do that, at least at scale or effectively, like the way we are able to currently do it. He said OpenAI should change their name to Close AI. Yeah, they're not publishing their research. Or they have some novel approaches. They've probably added some new parameters, some new layers that they've invented, doing some vector manipulation, or maybe adding some, numbers or subtracting some numbers, right? They have the best model out there, but nobody knows how they're accomplishing their results. It's really unfortunate that they're not sharing with the community what they're doing. It's really unfortunate. More questions? More questions? Four more minutes. Ask stupid questions. There are no stupid questions. Okay. I can see a lot of people typing, right? So check this what's it called? This notebook, so you could, I think this is the one, yeah. Try your hands on a different sets of words and check the similarity score using the dot product that we have here, so that you can have a fairly better understanding of how attention is happening between those words when we say, okay, similarity between this word and this word, right? You can also try other models, other word-based models. Of course, I mean, once you load this notebook, you can, save it as something in your own drive or your own GitHub, right? You can come here to these docs and come to the transformer and come to the text models, right? And play with any of these models, right? These are all funded by, open initiatives. And there you can, check them out. This is the one we used. This is the one we used. BERT, where is it? Right. So you can check out the embeddings that each of them generates. This is very interesting as well. Bloom is a very interesting one. We can't check everything out on in a class, but just play with them, and then also if you have some time, just try to play with, other models, vision models, vision transformer models. BEIT, BIT rather, was proposed as big transfer general visual transfer, visual representation learning by these folks. And then you can see the abstract. By transfer of pre-trained representation improves. Check it out. There's a whole lot of learning to do in terms of transformer because it's evolving really fast and people are improving it every day. And there's a very high chance that it will probably have better transformer, or not have a better approach that separate from transformer. We'll probably have better transformers in the future. So it's a very big domain. Yeah, awesome. So I saw you used PyTorch. Do we have to learn that too? No, not necessarily. Not necessarily. You don't have to go as deep as when you have to deal with it classically. So what I would do is that let's be looking out for the class email, add some other links, supporting documents, supporting video from other people explaining the word to word, text to text transformers, right? And then that can just, if you understand that so well, you'll be able to, wrap your mind around the other modalities as well. So awesome. Thank you so much. Let's have this week and let's look out for the class notes. Oh, Ngozi, today's your first class, Ngozi.
Yes. Good evening. Yes, today is my first class.
Thank you, Stephen. Ngozi, check out the classroom. Check out the Google Classroom. All of the previous sessions are available on demand. Right here is the Google Classroom. And we now have a YouTube channel as well. So if you want to download the video, go to YouTube and get the video.
Okay.
This is the classroom. This is the link to our Google Classroom. You'll see all the previous classes, all the previous lectures and all that in there. This is the link to our YouTube. I think this is it. If you would like to download the videos, you can use this as well. Thank you, Mr. Ayomide. Thank you, Mr. Samuel. Thank you. Guys, don't worry if you're confused about transformer. Just give it, spend some time, put a little bit effort, you will figure it out, especially with attached to the class notes. You figure it out. And build stuff, create your own notebooks, right? Use the docs, use Hugging Face docs, use Hugging Face models, read a few papers, that Hugging Face attached to the original author of those models, right? And you will find yourself building novel AI models or novel AI applications in no time. I am very confident that the winner of the 2023 hackathon would use a lot of transformer models. I'm fairly confident of that. All right, thank you so much. Let's have a beautiful week and let's look out for the class notes. Thank you very much. Have a beautiful weekend, everybody.